So welcome. So this is the 5th review session already, right? So I brought the apples as usual. We are going to, we just have 7 problems today, so maybe it's not going to take too long. But I think it's good we meet, you know, and we figure out how to do all these. I think there's a bunch of cyclohexane stuff, right? And Newman projections, some more. And that will set you all up for, you know, for the stereo isomer stuff you're going to talk about in next lecture. So in chapter 5. So who wants to try problem 1? Basically drawing a Newman projection along this indicated bond and then rotating the thing into the highest energy conformation. Give it a try. Okay, let's pick up some other color. Maybe this violet.
Okay.
Try. Let's see.
Oh,
sorry. I think we are in erase mode. No, it's fine. It's just was trying to paste something.
Okay.
You just have to. If you stay too long on one point, it will start to
select.
It
does weird things. Okay.
It selects what you draw.
Okay.
Perfect.
Oops. Oh no. Right? Other side? Other side, yeah. Thank you.
So, yeah, put H. So you have to put H wherever there is no carbon, right? So what you just drew, this is a great start. What you just drew is essentially this one. That's the one you just drew, because remember, whenever you draw just a thing like this, it means CH3, right? And you see when you look at the actual thing, right, it has a hydrogen attached on each, and these are CH3s. So you need, the safest thing to do is to write CH3 for 2 of them, and then H for the other one. So to try, see where they go.
So
you drew it eclipsed, which is great, right? That's the highest energy conversion. But now the question is, where do the CH3s go, and where does the H go?
So an H
relative to each other.
Would be here and here.
How many?
Or no?
Okay, so that's good. That's a good start.
And then everywhere else is a CH3?
Yes, that's a good start. So put that in there.
Okay.
That's a very good start. Now the question for everybody is this the highest energy conformation?
No.
No, because you see, why not? Because
those CH3s.
Let me draw it. Yeah. You see because you have a lot of eclipsing interactions now, right? So what type of interactions do we have? Here we have CH3 eclipsing, right? What's the energy cost for that? Do you guys remember? Oh, I don't remember. No, it's more. What did we write down in lecture? I don't want to give the wrong number. Did we say 11? Yeah. So that's 11. Let's say that costs us 11 kilojoules per mole. Okay? CH3 eclipsing. Now the other things we have here, you see, what are these? These are CH3H eclipsing. How much do these cost? 6. Okay? So now what can you do? Is you can take the front wheel and rotate it by another 120 degrees let me see. Yes, and then the H's will be on top. So let me show you. So we'll take it, rotate, front, okay? And what we are going to get looks like this. So the back part will keep the same. So it'll be CH3, CH3, right? We just leave it the same. But the front, we rotate. So now the 2 H's are on top of each other. And the 2 CH3s are on top of each other. So now let's calculate the total relative energy for this one. Right? So what's the energy cost here is plus 11. Right? Because that's CH3 eclipsing. This guy up here is also plus 11 kJ per mole. What about HH eclipsing? 4. Okay, so plus 4 kilojoules per mole, right? So what's the total for this one? 26, right? The relative energy of this conformation is 26. So I'll say relative energy equals plus 26 kilojoules per mole. What's the total energy for the other conformation? Say again. 23? Yes, so that's total energy equals 23 kilojoules per mole. So you see that the highest energy conformation is the one I just drew, right? This one. Okay? So it looks a little bit ugly, but you get the point. You see, you have to basically rotate things all around to really find the highest energy conformation. So it looks like a really easy problem, but actually it's a little bit more involved. Okay? You did a wonderful job getting us started. So you want 1 apple or 2 apples? One. Let's see. 1. We'll see. If I have extra apples, you guys can just take them in the end. Or I make an apple pie, like always.
Aren't there Gaussian interactions occurring between the CH3 and the H on the second one?
So that is a very good question. The question, I'll just repeat it for the video. The question is, are there Gaussian interactions between the methyl group and the H? Okay. So which methyl group and the H? I'll highlight it. I think I know which ones you mean. So you mean, for example, this methyl group and in the back and this H in the front, right?
No, I mean for the other structure that you drew.
The other one I drew. The one over here?
Yes.
You mean like between these guys?
No, I mean, wait. The CH3, the methyl group at the top.
Yeah.
And the H around 4 o'clock.
This one?
Yeah.
So it would be the one and this one and this one?
Exactly.
No, because the Gaussian interactions occur when the angle is 60 degrees. Remember, let me draw you, I'll see if I have some space here somewhere. I don't really, but I will shrink it a bit, okay, so we can get some space. Let's just shrink the whole thing. So a Gaussian interaction, remember, is like this. You will have front wheel, for example, CH3 over here, HH, and the Gaussian interaction occurs in the staggered conformation, right? Where you see where the methyl, and it really occurs between 2 methyl groups or something bigger than H. So if here this is H, there's no real Gaussian interaction here because the H is too small to have a Gaussian interaction. But if you have a methyl group right here, then you will have a Gaussian interaction. This would be gauche, right? So this would be H and H. So this would be gauche. But you see, the key here is a 60-degree angle. In the other one, we have a 120-degree angle, so they are further apart. That's why we don't consider Gaussian interaction. The other interaction there is really the ones because they're right behind each other, then it's an eclipsing interaction. Good question, though, right? Okay, so the Gaussian interaction only occurs in the staggered conformation when they're 60 degrees kind of apart from each other, and only between something larger, 2 things larger than hydrogen. Okay? Good question. Other questions? I'll get you an apple for this because it's a good question. Can you catch it? Okay. Other questions?
Sorry, I came in a little bit late, so I
Yes.
don't know if you answered this already, but why did you draw it in the eclipsing way rather than the staggered?
Why did we draw it in the eclipsing way rather than the staggered? Good question, because it says, you see the question says, we wanted to draw the highest energy conformation.
Okay.
And generally, if you want a really high energy conformation, eclipsing is a good way to start. Because the staggered ones are generally much lower. Those are always the minimum conformations.
Okay.
Right? That is why. Good question. Other questions? Okay, if not, let's move on. So you can still read it, right? It's a little chaotic, but I think it's fine. Okay, draw a chair conformation of ethyl cyclohexane with the ethyl group axial. Who wants to try? Let's see. You are nearest, so you can try it first. Okay, here we go.
Thank you.
Welcome. Should probably do that. Thank you. Here we go. You're welcome. So let's see, this is good. That was a pretty, does anybody have a question? Yes, please.
What happens if you flip both of them? Like if you.
Do you have another one? You want to try to draw it?
Yeah.
Maybe try your answer.
Like that. Like what's the, and then ET up here.
Can you try it? Let's go ahead and try it. It's a good question. So let's see. We draw it in another way. This is perfect.
Okay.
This is the correct answer. Okay. Except, be very careful. Your chair is a little bit. You see, your ET is tiny bit twisted.
Okay.
Tiny bit. Yeah. It's not a huge deal. This would still be fine on the exam, I think. But you know, depending on which TA looks at it, make sure you draw it super nice, the chair, okay? So that they have nothing to criticize. Thank you. But this would be correct. Yes.
If you ask this question, would you always want the flip version also?
No, not if I ask this particular question, no. Okay. But so we can go, you have another question? Yeah. You want to do the next one?
No. I was just wondering, like, can you just draw out the ethyl group?
Oh, if you draw out the ethyl group. Okay? So if you draw something like this. Oh, that's a really ugly one. Let's see. Here we go. If you do it like this, we'll draw it. Oops. See, I also have trouble drawing it, okay? So if you do it like this, for instance, yeah. Perfectly fine. Okay. Perfectly fine. Okay? So, hold on, was there another question I had to answer? No, that's it. I answered your question, right? So if I just ask for one chair conformation with ethyl cyclohexane axial, that's it. If you flipped it, right, you get the ethyl group equatorial. So then you don't really answer the question in that sense. So in this case, you don't have to. But I think the next question asks, you see, the next one asks for both chair conformers. Then you have to draw both. So it depends what I ask. Really depends. You want to try the next one? Okay, I'll go. Okay. Good. Thank you. Let's see. Did anybody get another apple? You guys asked the question. All right, let's see. All right. Yeah, so you drew the equilibrium arrow, right? You said that shows that the one with the OH equatorial is more stable. And that's it. That's perfect. Okay? Do you guys have any questions? Again, but still, you know, it's hard to draw on the iPad, right? But the chair here is a little wonky, you know. So just be very careful to draw it nicely, okay? Yes, do you guys have questions?
Do you want us to write this equilibrium thing to indicate which is more prevalent?
So the question is, do I want you to indicate the equilibrium arrow? Yeah, I mean, if I ask for it, yes. If I don't ask for it, probably not. So what I might do in the exam is I might give you like 2 boxes, you know? And I might even do something really mean like this, where I do like, look, like this.
Oh, okay.
And then fill in, you know, the structure. So you fill the more stable structure in the right box and the less stable one in the left box. And then I might do something like delta E equals, you know. And then you're filling the energy difference in there. You know, it really depends what I ask.
Okay, but that question itself doesn't require you to indicate.
No, it doesn't. Here I'm just asking to draw both chair conformers. Okay. Again, but this is just some, you know, for the problem set. In the exam, I'll try to be extremely clear what to draw, and generally I will ask you to draw it in some place. You know what I mean? I will not just leave you free form drawing like somewhere on the back of the page. because we will not be able to find it. So I'll be like in the box, indicate, draw this thing. And then first draw the more stable, or circle the more stable conformation. That's a thing I often do. And then part B could be like, what's the energy difference, or something like that.
Okay.
Does that make sense? So I'll try to be abundantly clear. Otherwise, our grading will be just a nightmare. Okay? All right. Should we go to the next one? You guys have other questions?
Yeah, so why is it that the equatorial is more stable than the axial for this?
Why is it that the equatorial is more stable than the axial? Good question. It has something to do with gauge interactions. Okay? We talked about briefly in lecture. I'll show you again. So if you, the easiest way to understand this is to look at the model, right? If the modeling kit, you build the chair, and then what you see is you should see the following. So I'll take off these boxes here because they're not too helpful for you guys. Let's take off the boxes, get some space. So if you, let's do this. If you look at, so we look at this conformation. Essentially what happens is the axial conformation, or with the OH group axial, that conformation is destabilized, that chair is destabilized by gauge interactions. Okay? And the best way to see it is to look at your model and to look at and then draw a Newman projection, okay, of the chair. So how we do it is we draw a Newman projection, for example, looking along, two parallel bonds, right, in cyclohexane, like these two guys. And so you will look, for instance, let's look along here and here. Okay, so then the way it looks is you get this wheel, you get the two wheels, right? And let me do this. It's hard to see it in this way.
Yeah.
So if you draw the OH in a different way, it will be easier to see. Okay, so what I'm going to do is I'm going to redraw the chair with the OH axial. Yes, so we're going to do it like this. Just going to move the OH to a different position. Okay, so I'm going to say, all right, it's still axial, so and still up. So we're going to put it, for example, over here. Okay, and now what we can do is we can look along these two bonds. Okay, in the Newman projection, that will be easier because you can imagine looking along like this from that side. So we'll draw the two wheels, right? We're looking at it from the kind of from this side, from the left. And so what's the front part of the chair? That's pointing down like this. You see this corner here is pointing down. So basically this group here is what I circled here, this CH2 group. And then the back part is pointing up. Okay? Now what we have is on the left side we just have H's. See that? So there's no gauge interactions there because it's just H. But on the right side, you see this is an H and this is the OH. Oops, and then this is of course down, that's axial. You see that? So that's the Newman projection. And now where is the gauge interaction? The gauge interaction is between this OH and this CH2. You see these guys are like next to each other. And that's a gauge interaction. There is another gauge interaction. And that's on the other side of the molecule, but you would have to draw a different Newman projection to see that one. So don't worry about that one. So the answer is because there are gauge interactions when it's axial. If it's equatorial, right? What happens is then the OH will show up here where the H is. And you see then this group and this group, they are anti to each other. They're on opposite sides. So there's no gauge interaction. So that's why the axial one is less stable. The other way you can explain it, which is actually similar, is you can say, all right, here you have, it's called 1,3 diaxial interactions. You know, where these groups are kind of repelling each other in the axial conformation. So because this is kind of big, this is kind of big, so they're bumping into each other here, and this is called a 1,3 diaxial interaction. We mentioned both in lecture. The 1,3 diaxial interaction is not as, because the hydrogen is kind of small. doesn't really explain much. What it really is a Gaussian interaction. You see that in the Newman projection. Okay, does that answer it? So there was a long answer to a short question. But this is among the hardest things to understand, so I like to discuss it over and over again. At least what you can do now, I think, is actually draw Newman projections of chairs, right? You guys feel good about doing that? Which is a pretty good skill to have. Okay, another question, or you want to do? Yeah.
Sorry if this is irrelevant, but is that other Gaussian interaction between the CH2 that's, I guess, completely opposite from the OH?
Yes. So I'll show you the two Gaussian interactions. They're here. One of them, right? The one we already drew is this one. Hold on. The OH, like this, like this. This is one of the Gaussian interactions. The other one is going in the other direction. So if you look along this bond, that's where you find the other one. So if you do the model, you build the model, you will see them. Okay? Keep practice. It's very hard to see them. All right. So why don't we move on to the next one? But those will keep spending all our time with this. Okay. So we need to draw the most stable chair conformer of the following, of this molecule. Let's see. You did one already. Okay, we'll get you to that. Okay. Let's see. We go back to this one. Okay. Thank you. Good. Nothing to say. Yeah, you guys have a question? You want to try yours? You try yours. Yeah. Here we go. Okay. Maybe zoom in a little bit with 2 fingers so that we have more space. Pretty good. That's fine.
Okay, cool.
That's fine. It doesn't matter. You see, as long thank you. As long as you draw the 2 substituents, like if you draw the isopropyl in position 1 and the oxygen in position 4, you're fine. Right? What you don't want to do is you need to have enough carbon atoms between. That's very important. But otherwise, in this case, the stereochemistry doesn't matter too much. Like where exactly you draw it doesn't matter. Where you start, as long as the distance is correct. Okay? Yes?
How do you know what angle to draw the substitution
Why can't you point straight down? You mean like, let me see, for instance, like this. I'll draw it in like light yellow, like this.
Yeah.
Because the question asks for the most stable chair conformer, right? Yes, it has to be equatorial, because the big substituent, right? What the only thing you cannot forget, the most important thing from this chapter is an axial substituent is less stable than an equatorial one, right? So if you have something like an isopropyl, which is a fairly big substituent, you want to put it equatorial. That's why. Because it asks for the most stable one. If I didn't ask for the most stable one, it would be fine. Question? Yeah?
Is the oxygen in the axial or equatorial position, or is it kind of just...
It's neither. So the oxygen, the question was, is the oxygen in an axial or equatorial position? It's neither.
Okay.
Because the oxygen is part of the ring. Okay? Only a substituent can be either axial or equatorial. So what happens to the oxygen, though, which is interesting, is it has 2 lone pairs, right? It has 2 lone pairs. One lone pair is axial, one lone pair is equatorial. So this would be the equatorial lone pair. And then you have an axial lone pair. Okay? You see, because kind of the lone pairs act like the substituents. Right? If you have a carbon, you have two substituents attached. If you have an oxygen, because the oxygen in a neutral form only makes two bonds, so you have just two lone pairs which are pointing either axial or equatorial. Does that make sense?
Yeah, so the isopropyl, so the isopropyl is the only thing that really counts in its stability at position?
Yes.
Okay.
Yes, the isopropyl here is the only thing which counts, which is why this is still a fairly easy problem, right? Because, as we've seen in the lecture today, there's sometimes I give you two substituents. And once I give you 2 or 3 substituents, then it becomes more complicated. Okay, then you have to pay more attention. Then many things start to matter. In this case, just with one substituent, that's just the isopropyl which matters. Do you guys have other questions about this one? Good, let's go on to the next one. So now we have more substituents. Okay? Draw the most stable chair conformer of the most stable isomer of 1,3,5 trimethylcyclohexane. So this is a complex question because, so first of all, you have to draw 1,3,5 trimethylcyclohexane. And there are different isomers. There is the one where, all of the 3 methyl groups are cis. Then there is one where 2 methyl groups are cis and the other one is trans, right? So for example, up, up, down, and you have up, up, up. And you need to figure out which isomer is more stable, which is the most stable altogether, and draw the most stable chair conformer of that one. So who wants to try that one? That's a more tricky one. Tricky one. We give it a try. Good.
Thanks.
The way to do it, just try your way. Let's see.
Yeah, well, I have to remember how.
Oh, yeah. What you do is you first draw a chair, right? And draw a chair. Good. Let's try to.
Sorry, yeah.
Let's try to connect those lines.
How do you
Perfect.
erase?
I'll help you. We
Right.
could just erase it, this guy. It might be too fat, so we make it a little bit nicer. So we can just go like this. That's pretty good.
And then I'm going to put them in.
Let me put this again so we can. Okay.
I'm going to put them in the equatorial position.
Yeah. So yeah, exactly. That's the strategy
Is
you
the
want to do.
point I'm
You
getting
want to
at,
do
yeah.
it. You want to put as many of these methyl groups, right, in equatorial position. So start off with one in equatorial. Perfect.
So that's
and now
one.
the others go where? In 1, 2, 3 positions, right?
Yeah.
Yes.
And then, but the parallel part is the confusing.
Yeah. So try to draw it parallel. The other direction. Sorry.
Other direction?
That is. Yeah. You have to go up left.
Up left.
That is hard. It took me a while to figure that out. The first one. Yeah. You have to go up left. Let me see.
Yeah, sorry.
It just when you it's selected, the thing, so you can copy it if you want, but you don't want to
Gotcha.
copy it. So you see, you have to be
Go like that.
parallel to this guy,
Okay,
or actually parallel to this guy. So
Right,
you're
yeah,
going
yeah.
like this,
gotcha.
right?
Yeah.
So on the outside corners, you want to point outside. Okay, good. And now there's one more.
And it'll be parallel to.
Yes, parallel back there. Yes,
Okay.
yes. Oh, good question. Let me answer.
Oh
that in a
yeah,
second.
that is actually.
That is a very, very good question. I will answer it in a second.
Hash
The answer is no. Never.
No.
If you draw a hash, bad. Okay?
Okay.
So give me 1 second. So this is correct. Okay? This is the most stable isomer of 1,3,5 trimethyl cyclohexane because 1, 2, 3, 4, 5. You see it has put methyl groups in position 1, 3, and 5. And all of the methyl groups are equatorial. That's why it's the most stable. Okay? Very good. So can you draw me a line drawing of the thing?
Sure.
Just, on the side, just so, for completeness.
And then pick, you just.
Yeah.
And with the wedges and dashes?
Yes.
Or, okay.
Yes. Here, in the line drawing, you put wedges and dashes.
Well, now I don't know which one. Now
It
I
doesn't
don't know.
matter if it's
Oh,
pointing up
okay.
or down, because
Okay.
it just means you would rotate the whole molecule around in the board, right? Yes. So you do like this, And then you do another. Perfect.
Well, okay.
You don't even have to
Yeah,
write
you
methyl.
don't, but-
You could just leave it, but you can write methyl, that's fine.
And then ignore that little tail there.
Yeah, we'll ignore the tail. So that's it. Good. So what I'm going to do is just I'm going to adjust it a little bit. The upper one here I want like to be, in this case, it should be, you know, just nice and straight up here. You see like this.
But doesn't that contradict the equatorialness of it?
It looks like it's
If they're all sticking out in the same direction?
Well, yeah, in the line, so that's why I'm drawing the line drawing. So this is how the line drawing looks. The line drawing has nothing to do with equatorial or axial. The line drawing just tells you whether they're pointing up or down, right? And you see here, even though they are all equatorial, if you think about the hydrogens here all pointing down, right? You see that all of these methyl groups are actually pointing up.
Okay.
And that's all the line drawing tells you, is that all the methyl groups are pointing up. It doesn't tell you anymore.
Yeah.
The line drawing has nothing to do with the real geometry of the thing. Okay, because it's basically flat, a flat ring, which is not, right?
Yeah.
But that's just the line drawing just tells you they're all up.
Yeah.
So back to your question, right? Is it can you draw dashes and wedges on the chair? Don't. Try not to. At least directly for the substituents coming off of it. The chair you shouldn't, because the chair drawing already implies, you know, the direction where the substituents are pointing to. Okay? There might be some special occasions where you might be able to do it, but I would rather you don't do it, because it's not the safest. If you draw the dashes and wedges in the wrong way, and it's going to be bad. Okay? So no dashes and wedges for chairs. But for the line drawings, yes.
I have another confirmation. Can I draw?
Yeah. You can draw that one. Let me see. I'm gonna shrink this stuff a little bit so you get some space. Okay. Here we go. So we're gonna get an alternative solution. We're gonna make it in green. Okay. Here we go.
Thank you.
Yeah. I gave you an apple already. Do you want an apple? If you want. This is good, except you see this substituent here.
Yeah.
It's fine the way you draw. I mean, you want to draw it like this.
Oh, that
You see out, and the other one here a little bit more,
one. Okay.
a little bit more angled, less angled. Okay, so it's really equatorial.
How do you, know?
Which way?
Yeah.
This basically you just have to memorize from the book. Just draw like hundreds of chairs, okay? And then memorize the way it's drawn. It's basically pointing outward for the ones more on the outside, okay? Just memorize drawing the chairs. Practice drawing in all the substituents on the chair, okay? Like we did in lecture and like the book does it. That's the safest way, all right? Do you guys have other questions? One more? Yeah.
I thought that the trans conformation was more stable than.
Uh-huh.
So why wouldn't you have one of the methyl groups up so that it would be trans instead of having them all be on the same?
So if one of them is up, right? If you flip one of them, then that one has to be axial. And you see, then you have the cost of having a methyl group axial, which is what? It's like 7.6, right? kcal per mole? Kilojoules per mole? Kilojoules per mole, yes. And so then that will cost you extra energy.
So axial and equatorial matters more than trans and.
Are you saying that trans is generally more stable?
Yeah.
Why? Was the book saying that, or
Yes, that's what I thought.
is it for? But that's probably for. So the question is: are trans generally more stable compounds than cis? I think that's true for double bonds. So if you have something like this, the trans is more stable, right? Because now here it's all sp2 hybridized carbons here, and so they are in the plane, right? So here trans, you see the methyl group here. If we draw in the hydrogens, you see the methyl group is fairly big, and so here the trans conformation is more stable than the cis, because you see the cis. Sorry, this is like wedged here. So the cis is, the two methyl groups are kind of bumping into each other. You see that? And I think that's what the book is referring to. So here, the trans is more stable. But that's for double bonds. That's different than for the rings, okay? So you can come up with situations where the trans is more stable. Can anybody think of a ring where the trans is more stable than the cis?
It's got two.
So for example, something like this, if you have a cyclobutane, okay? Like this, if you have a cyclobutane, which is more flat, and these are the substituents, now they are eclipsed. You see that? Now here the trans would look like this. And here the trans is more stable. Because you see, if you look along this bond here, right, these substituents are eclipsed in the cyclobutane. Because it's a four-membered ring. It's not like twisted like a chair, like the cyclohexane. Okay? So in this case, the trans would be more stable than the cis. But in the other case, also because it's in the cyclohexane case, because it's a 1,3 arrangement, so you have always a CH2 group in between, so they're not right next to each other, these methyl groups. That's why the equatorial, then being equatorial is more important. Does that answer? It's a good question. All right. Next one. Let's move. One question. You want to do the next one? Yeah. Okay. I'm just going to go to the next one. Cis diethyl cyclohexane. Let's do this one. Here we go. Okay. All right.
Yeah, I'm gonna draw.
Good luck. No, I don't know how hard it is.
Oh no.
Just can't remember. I figure out how hard they are when we do it. Okay, good. That's this. So hold on. This is dimethyl cyclohexane. So perfect.
So they're both equatorial.
Okay, I'll give you an apple,
Okay.
and then let's discuss it.
Okay.
Very good, thank you. So, what you drew? What did you draw? Let's look at what's on there. Okay, if we draw in the hydrogens, all right, you drew them in 1, 2, 3, 4, 1, 4 substituent, which is great, right? So the one you drew on the left, you see this one is great, okay? Because you see, they are cis, right? So they are pointing, this is pointing up, and this is pointing up. Okay? That means cis. And that's what we want, because the name says cis. Okay? And you drew them 1, 4, which is also what we want, so that's great. And you drew a cyclohexane, which is also great. So now, what did you draw on the right side? You see, we can draw in those hydrogens, right? On the axial positions. Now, how are the hydrogens pointing? This one is pointing up. This one is pointing down. So what about the substituents? You see, this one is pointing, what, up or down? Down, right? This is down. And this one? Up, right? Because the hydrogen is pointing down.
The ethyl on the right should be in the axial.
Yes.
Okay.
It should be in the axial. It has to be. So you see, this is a very trick question because, I just told you always need to draw the substituents equatorial, if possible, right? But here it's not possible because they're cis. If they are 1, 4 apart, they cannot be cis and both in the equatorial position. One has to be axial.
Okay.
If they are in a 1, 3 arrangement, like 1, 3, 5, or 1, 3 dimethyl cyclohexane, they can both be cis. Then they can both be equatorial.
So,
But then 1, 4, one has to be axial and one has to be equatorial.
so is what I drew the trans?
You drew the trans.
Okay.
So we will say this is trans, right? So the cis, I will draw the cis. The cis looks like this. Sorry, long answer, okay? I always give long answers. You guys might have figured it out by now. Let's see, so the other one. So what I would recommend, here's how I recommend how you should do it. You see, what you did really well is you drew this other thing first, the line drawing, right? To make sure you're drawing the right thing before you start drawing a chair. You make sure you know what you're going to draw. Okay? So what I would do is you see that the first one is pointing up here, and the second ethyl is also pointing up. So I would both draw them up, like you drew in your line drawing, to not confuse yourself. So you can, for example, say, and you see you started drawing the first one down in position 1. So I would say you say, okay, 1, 2, 3, 4, right? And okay, it was up on the left, so we're going to do this one up as well. And then the other one was up, so we're going to do it up here as well.
Okay.
That's the easiest way. Okay?
Okay, cool.
Good job. So did you get the apple?
Yeah.
Okay. So do you guys have any questions? It's very, very important. You see you have some constraints on what you're going to be able to draw based on where the substituents are and whether they are cis or trans. Yes?
Is that why the trans overall is more stable than the cis because it can have both in the equatorial position?
Oh, yes. In this case, absolutely. The trans would be more stable. Would be more stable compound. But because I'm asking you for the cis, you can't draw me the trans. Otherwise you have a problem. You know what I mean? That's exactly what's happening. So it is really tricky. It's just kind of it's like finicky on what I'm asking and giving me exactly what I'm asking for, right? So why don't we do the last one? Okay, I think there's only 7 questions today. Here are the questions, which is more stable? It's actually related to what we talked about. But it's switched. It's switched because now there are no more 1, 4. Yeah, what do you think? The cis is more stable. Must be because the 1, 3, 5 was all cis, right? Okay, so the left one is the trans. The right one is the cis. Okay. Sorry.
I don't need another one.
So let me. So you say that trans is more stable. Okay. Because one of them is.
Another apple.
Are you sure? Okay. You might need it after. after I tell you your answer is not right. So look, this is actually a harder question than I thought. Okay? Why? Because, so now look what I'm going to do. Is I'm going to take the thing you have, the cis, and I'm going to do a ring flip. Okay? I'm going to do a ring flip. So you're going to take this corner, flip it down, take this corner, flip it up. Okay? We flip the ring. Now look what happens.
It's going to be equatorial.
Now both suddenly become equatorial.
So that's more stable.
Yes. You see, it's going to look like this, which is now more stable. So what I'll say is, okay, this is even more stable. So the correct answer is the cis. You see how tricky this stuff is?
Yeah.
This is really tricky, okay? You see, you have to consider, why is it so tricky? So what happens if you do the ring flip from the trans? You still get one equatorial and one axial of the methyl groups, right? It doesn't change anything. But you see, for the cis, it matters. You have either both axial or both equatorial. So you have to consider the ring flip when answering this kind of question. You have to always consider both possible chair conformations for whatever you are drawing. And it's very tricky. Believe me, you saw that, okay? It's really tricky. So you need to practice this stuff. It's kind of, I think if you practice it well, you have a very good chance of getting the problems right on the exam. If you don't practice it, you really risk getting it wrong. And it's going to be, these kind of questions are gonna be like, 6 points there, 8 points there, You know it, you get the points. You don't know it, you lose the points. It's really gonna make a huge difference. So just do practice problems, come to my office hours if you have questions, okay? Post stuff on Piazza, let's keep working on it. You guys are doing a pretty good job. I think you're getting the hang of it. And I'm hoping people will at least watch the review session who were not here. Because you saw the room, how full it is during the exam. All right, thanks guys for coming. I have a couple extra apples if you want one, okay?